Okay, thank you very much. Thank you for the invitation to this very exciting conference. Really learning a lot of interesting things. So I'm going to tell you about some recent work with postdoc at Harvard, Alex Khrushchev, my former student, Avishkar Patel, and recent discussions with two experimentalists at Harvard, Philip Kim and Ameyo Kobe, where we are trying to see if there's some way to implement these ideas in their laboratory. So let me just begin with some general discussion, which may be unnecessary given all the talks that I've talked about the same thing. But I'll just show you my little simulation. So here's a toy model of a typical metallic grain, a small metallic grain. This would be not an unreasonable model to even study details of many experiments. So you have a bunch of sites, say n sites, which fraction of which are occupied by electrons. And you allow these electrons to hop from one side to the other. And the matrix element of every one of these processes is just a random number. So that essentially the Hamiltonian is just a random matrix. And that's kind of the bad guy. That's the model that we don't want to have in our laboratory, but it will be present to some extent, and we want to also understand its properties. Okay, so these are the good guys. So now you take the same system, and you now allow the electrons to move in pairs. So every one of these processes entangles the electrons, and the amplitude for any such allowed process is just a random number. So that's a simple graphical representation of what people are calling the SYK model. This is really the complex SYK model because I'm not talking about Majorana fermions here. I'm talking about a model in which the fermion number is conserved. So that's going to be crucial to everything I'm going to talk about, and also to the experimental probes I'll discuss. We're really using the fact that the electron number is conserved to even define the probes. Okay, so this model is solvable and has been used to describe strange metals and also black holes, as we've heard yesterday. All right, so let me just summarize. So here's the actual equations. You have some random interaction, which I'll call U. Alpha, beta, gamma, delta are some sort of orbital label. So U's are all independent random numbers, and root mean square value is U. Now, in this model, unlike the Majorana model, there's another energy scale, and that's the chemical potential mu. And as you vary the chemical potential, the charge density Q, so this is the average density of electrons, it has to be between 0 and 1. It's a conserved quantity that commutes with the Hamiltonian. Will vary between 0 and 1 as you vary mu across its values. So there's actually a dimensionless number characterizing this model. That's the ratio of mu to u. Okay, so what we know about this model is that so we can think of this model having no dispersion. So there's really effectively a flat band. There's a random interaction, and that's the density. Okay, so this model is solvable in the large n limit. And what we know from various numerics is that it describes a critical phase. So this is also a difference from the Majorana model. There's a whole line of critical points over a range of values of mu. You can't make it too large. Q has to be close to a half. But there's numerically clearly seen a stable line of critical points. And we want to understand the properties of this critical phase and possibly realize it in experiments. So what are the properties? So if you look at, for example, the two-point fermion correlation function, that decays with some anomalous exponent, which can be computed exactly with the square root of time. But another feature of this, which is not present in the Majorana model, is the particle-hole asymmetry. You can think of the amplitude for positive time as the amplitude to add a particle, and for negative time, the amplitude to remove a particle. Now, if Q is close to 1, almost every site is occupied, it's much harder to add a particle than to remove a particle, and of course, vice versa. So therefore, the amplitude for adding and removing need not be the same. And we parameterize in this strange way by this factor, e to the minus 2 pi squiggly e. So the value of e varies as you vary q, which is this dimensionless parameter that characterizes the model. So that's what happened. There's a line of critical points. The exponents don't change. They could have changed, but they don't. They're the same everywhere. but this amplitude is a smooth function of q, and in fact, it can be computed exactly. So that's kind of a IR-UV relation, because E characterizes the IR asymmetry, Q is the UV asymmetry, but they can be related exactly by some rather subtle arguments, and going through those arguments are in these not so recent and recent papers in some detail. Okay. All right, but we don't need that relation, just need to know that it's there. Okay. So those are two crucial properties. Now, one thing to note here also is that this type of IR particle-hole asymmetry is quite an unusual thing. It's not present in a Fermi liquid. So if I took the simple model with one particle hopping, that does not have an IR asymmetry. When you're close enough to the Fermi surface, particles and holes behave approximately the same way, and at long times, they both decay as 1 over tau with the same amplitude. So it's only this non-Fermi liquid or non-quasi-particle system that has the room to have a particle-hole asymmetry that's so strong. And that's really one of its key properties and leads to many of the anomalous features, including the black hole-like behavior that I'll show you in a minute. Okay, so another key property is this property, which informally is a violation of the third law of thermodynamics, that if you take an infinite system, the entropy density as temperature goes to 0 after you've taken the infinite volume limit is a non-zero constant, which I call S0. So this constant depends on Q, and in fact, we can compute it. So let me just show you a few pictures as to what this means. If I took the simple model with one particle hopping, but thought of it as a many-body system, and I'll have 2 to the n levels, and all the levels are just sum of the single particle states. The 2 to the n comes from the fact that n alpha can be 0 or 1, and E alpha has the eigenvalues of an n by n random matrix. So there's 2 to the n levels over a bandwidth of order n. So roughly speaking, the mean level spacing is 2 to the minus n. But when you get to the bottom of the band, the spacing is much higher. The spacing is 1 over n. And this is really a characteristic feature of any system with quasi-particle excitations. This happens because when you're at the bottom, the ground state has some of these E alpha occupied and the positive ones not occupied. So the only way you can create a low energy excitation here is to take the last occupied level and move it to the lowest unoccupied level. That always costs an energy 1 over n, not e to the minus n. So because the energy level spacing at the bottom of the band is so much larger than in the middle of the band, the entropy vanishes, or at least the entropy density, entropy of a particle vanishes. And that's the third law of thermodynamics in action. Now, what happens in the SYK model is something very different. The energy level spacing is exponentially small everywhere, and even at the bottom of the band. And the spacing now is e to the minus n s naught, where s naught is this zero temperature entropy that I had over here. Okay. So that's one important property, the presence of a non-zero zero temperature entropy. But this entropy depends on Q. And another remarkable relation is that the derivative of the entropy with respect to Q, so this is a purely thermodynamic quantity, is exactly related to this particle-hole asymmetry that I introduced earlier. And I'll shortly give you a hand-waving proof of where this comes from, but it's very much related to the non-Fermi liquid aspect of this problem. So, but this also shows you now that S naught is non-zero at temperature goes to 0, this is a non-zero number. The presence of a particle-hole asymmetry is intimately connected to the fact that there's a non-zero zero temperature entropy. Okay. Now, one other important property is everything I've told you so far. The nature of the Green's function, the particle-hole asymmetry, the zero temperature entropy, and this relation also apply to charged black holes with the ADS2 horizons. In fact, this relation was obtained from Einstein's equations and the Maxwell equations by Sen a long time ago, studying ADS2 black holes. Although actually it appeared in our work without any connection to black holes a bit earlier. And it's really the same relation because after all, this SYK model is as we now know in some detail, dual to the quantum fluctuations of the ADS2 horizons. Okay, so now let me just give you a quick hand-waving derivation of where this relation comes from the quantum mechanical point of view, not from the Einstein-Maxwell equations. If you take this Green's function I showed you earlier with this particle-hole asymmetry, and you conformally map it to finite temperature, this is the kind of form you find. Now, this sine inverse square root, it looks very familiar, just as any conformal field theory. This is perhaps a little less familiar. It's just an exponential factor, and it's just associated with the way the global U1 charge combines with the conformal transformation. So it has to be this pure exponential with this same E over here. But now if I stare at this form, it seems you can interpret this pure exponential as just a shift in the chemical potential. So this suggests that the chemical potential is a linear function of temperature, and this correction here is exactly this term over here. Okay, so if you now that's not an entirely rigorous argument, and there's various ways of justifying it. I mean, these equations were written down a long time ago, and the recent paper with Yingfei Gu and Grisha Tranopolsky and Alexei Kitev give perhaps the most complete argument for why this is correct. Okay, and it also falls out from the black hole solution, exactly this result. But now you can see where this relation comes from, because you have a Maxwell relation. This is pure thermodynamics. This is the key to everything. The Q derivative of the entropy is the same as the temperature derivative of the chemical potential. So now you see right away how you get this. You just take d mu dt from this equation. This is at fixed Q, and therefore ds dq is 2 pi e. Okay. And this whole thing can also be obtained from the equations of gravity. Okay. All right. So now this relation, now let's turn to some experimental possibilities. This relation ds dq is d mu dt is also crucial to some experiments. So in fact, here's a fairly recent experiment by the group of Josh Folk, where he's measured the entropy of a single spin. So what he's got here is, there's the spin over there, that little dot. I can't quite see over there. So there's a little dot with the spin over here. It's coupled to a reservoir. This is what's heating the spin. You're changing the temperature from this current that you put through this reservoir. And you apply a voltage to this little dot. And as you change the voltage, you see the number of electrons, the charge on the dot change. And you have this quantum point contact here, which the current flowing through that can tell you something about the charge on that dot. And so the whole thing is a very clever way of measuring the chemical potential on this dot as a function of temperature. So then, using this equation, you can integrate this and compute the entropy, starting from charge Q equals 0. And as you can see in this beautiful experiment on a single gallium arsenide quantum dot, you put a single single electron spin, and so an entropy of kb log 2. All right, so there's a direct measurement of entropy of just a single electron. So now the hope is that you can do something like this to the experimental system that Marcel Franz, one of the experimental systems Marcel Franz talked about yesterday. So in this case, you take a flake of graphene, small enough so that its boundaries are very irregular and they affect the bulk properties. Now, and you put it in a magnetic field. So in a magnetic field, graphene has a 0 energy Landau level. So effectively, the magnetic field has essentially turned off all the two-body hopping, but it's a flat band. And then the irregularities in the boundary hopefully give you sufficiently irregular interactions that they're perhaps in the same universality class as the XY model, which is fully random. So some of the things that Brian talked about yesterday of not having a completely fully connected model of being sufficient will, of course, be important for this kind of realization to be actually in the same universality class. Anyway, so what you have to do is to take this system and just put it in here and just measure the chemical potential as a function of temperature. And the key then, which is that the special property of the SYK model is that d mu dt will be a linear function of T as temperature goes to 0. So if you take a Fermi liquid, ordinary metal, the mu dt vanishes as temperature goes to 0 because mu is a quadratic function of temperature. So the moment you have d mu dt going linear as a function of T, then ds dq is 0 at T goes to 0. And then simply by integrating this, you can measure the entropy, which is, in the dual picture, that is precisely the extremal entropy of a black hole. So really what you have to do, and Amelia Kobe is thinking about these things, measure linear NT dependence of mu as temperature goes to 0. Okay. All right. So that's one possible probe of the entropy, just by carefully measuring the chemical potential of one of these flakes. So then let me also say something about another possibility. So that's thermal power. So what is thermal power, you ask? I can assure you I also had to look this up on Wikipedia. So what you do is you take a little grain and you couple it to little leads and you apply a temperature difference. Now, if your particle holds symmetric, if you apply a temperature difference, there's never going to be any charge flowing because particles and holes will react in the same way to the temperature difference. But if you have any particle-hole asymmetry at all, if you put a temperature difference, you can get a voltage difference. You can get currents flowing. This is, of course, thermoelectricity. So you take a situation where the currents, you apply a temperature difference, this charge start moving around, and then they accumulate, and then there's a voltage difference which completely cancels the charge flow, so there's no more current flowing, and you measure the voltage difference. So the ratio of the voltage difference that you measure and the temperature gradient is the thermal power. And it's easy to see it has units of kB over E. This is just nothing to do with quantum mechanics. kBT is energy, E delta V is energy, therefore it's just a pure number times kB over E. So you have to measure this number. Now this number turns out to be closely connected to entropy, which is not surprising because it really has everything to do with temperature differences. And it's also connected to changes in voltages, which connects it to changes in charge. So in fact, this number is just ds dq, the same quantity that I've been playing with. So if you take this particular model that many people have studied, Xiaoliang Qi proposed models like this a while back, and Douglas Stanford. So you've got each one of these is an SYK island, and they're connected to each other by either single or multi-particle hopping. If you compute the global thermal power of something like this, you find that it's exactly ds dq. Alternatively, you can take a charged black hole in higher dimensions with an ADS2 horizon, and then use the equations of motion to compute the thermal power, and you find it's also exactly ds dq. So the relationship between theta and ds dq is a general property of charged black holes and also SYK models of various types. Okay, but that's not what we're going to do. We don't have a lattice of them. It's hard enough making one. So what you want to do is take, the thermal power, of course, because this is non-zero. Again, the special feature of the violation of third law of thermodynamics, then the thermal power will be non-zero as T goes to 0. What we're going to do is take one of these and couple them to leads. And then what happens if you try to compute the thermal power in this configuration, just compare this formula and that formula. Here you had two powers of the imaginary Green's function. That's basically coming from the fact that the current operator takes you from one SYK dot to the other SYK dot, and each one of those ends up giving you a Green's function. Here, you're going from one SYK dot to a normal metal, and we just assume the normal metal has a constant density of states, so you get only one power. So the only thing that changed was one power. Now when you do this integral, you get this extra factor of 2/3. All right. So there's a slight difference, but it's still a measure of ds dq. So what you really have to measure in this configuration is the thermal power that's non-zero as temperature goes to 0. If you did this for an ordinary metal with one particle hopping, you can just do the calculation. It's still ds dq, but now because the entropy vanishes as temperature goes to 0, this will vanish as temperature goes to 0. Okay, so that's all, just basic and fun solid-state physics. What you want to do for the experiment is something more realistic. So this, probably is a pretty good description of the experiments, I would bet. It's just a question of numbers now. So you want to take a dot with both one-particle hopping and two-particle interactions. You also want to put in the tunneling between the dot and the leads. That's characterized by this number gamma. So now you have various energy scales. You have gamma, you have the root mean square value of the one-particle hopping h, and the root mean square of the interaction u. And of course, you want to be in a regime where u is much bigger than both h and gamma, because then you're going to see the physics of the SYK Hamiltonian. So now this is a kind of Hamiltonian in general is impossible to solve. But when h and u are random numbers, you can solve it. It's a little more work than the pure SYK model, but it's just something you put on a computer and just solve it, and therefore compute the thermal power. So let me just show you a few results of that. So for example, in the limit of very small coupling to the leads, this is the temperature dependent on thermal power. And now the key thing to notice is this energy scale, EC. So what you expect in this model is that if you're high temperatures, first of all, you want U to be much bigger than H, which we always assume. If that's not the case, it's hopeless. So U is much bigger than H. And then you're in a regime, temperatures of order U, you should see kind of SYK behavior. You keep lowering the temperature, you might think that when the temperature becomes of order H, then you're dead. But actually, it's much better than that. The temperature can go all the way down to H squared over U. And then only then you start seeing the Fermi liquid behavior. So when T over EC becomes of order 1, then it goes down to 0 temperature, vanishes at low temperatures. So in any real experiment, you'll always have this regime. It's just a question of can you find a wide enough regime where it's roughly independent of temperature. Lots of other things could happen in a magnetic field on a graphene flake. But if it's sufficiently random, it's hard to believe, at least to me, that it won't be somewhere described by some Hamiltonian of this class. So let's see how that works out. You can also look at the effect of the leads. You need the leads to detect any effect. So you turn gamma non-zero. So that's the T-independent regime. If you make gamma non-zero, you see it affects, for a while, it doesn't affect things too much. This value seems to come down. But if you make it really large, well, the temperature-independent regime survives, but the value comes down from this value you expect from a pure SYK Hamiltonian. We don't really even know the value of E, which is somehow related to the particle-hole asymmetry, which depends on the chemical potential you apply on the dot. Anyway, so I think there's a lot of variables here and a lot of experimental knobs to tune, so let's see how this goes. And I think hopefully in a few years I'll have, well, not me, but others will have some experimental data to compare with this theory. So this is somewhat earlier work where we are applying the SYK model to an actual metal, to experiments. There's no direct connection to black holes because, as we'll see, the kind of black holes we require a whole ensemble of black holes, each with a different charge, which seems totally unphysical from the gravity side, but it seems to be exactly what's needed for these experiments. Okay, so sorry, Daniel, there's more than one picture on this plot. So this is just to show you twisted bilayer graphene has nearly flat bands, so maybe it has something to do with SYK. And what people have observed, even in this latest hot off-the-press quantum material system, is that above the superconductivity, there's strange metal regime where there's resistivity that's linear in temperature. In fact, this linear in temperature behavior down to very low temperature has been studied in great detail in the last few years in a variety of systems. And some strange regularities have been observed. In particular, if you take this resistivity and you use the Drude formula from the 19th century to convert the resistivity to a time, this is something Drude derived for classical physics. It turns out to apply also unchanged to Fermi liquids. for sort of fortuitous reasons. And so then here you know n and e, and m star you read off from some other experiment, and so you can convert rho to a time. So when you do this in a wide variety of materials which show linear in temperature resistivity down to low temperatures, you find that the 1 over tau you get is almost exactly kV T over h bar with a constant of order 1, which happens over many systems with many different energy scales. Magic and graphene, TC's a few Kelvin, and cuprates is hundreds of Kelvin, and cold atoms is a whole different range. You get behavior of this type. And here's an actual numbers for a whole round of compounds. Alpha is this number here, and you see it's within a factor of 2 equal to 1. Okay, so we want to understand this. I can't claim we have, but we're going to give an ansatz, a very simple ansatz that seems to capture exactly this behavior. So what we do is we start out with this Green's function of the SYK model that I wrote down earlier. This is exactly the same expression. All I've done here is I've written this number E as a function of the chemical potential. And when the chemical potential is small, it's just clearly just a linear function. And numerically, you can get the coefficient C is a 0.41. So this is telling you that if you think in terms of the energy, think of E as an energy of the electrons, bare energy before they interact with each other, then this energy is the same. So every electron has the same particle-hole asymmetry. And that seems like too strong an assumption, because all of these materials have a Fermi surface. You can see it even though it's a strange metal. You can at least see a broad outlines of a Fermi surface in various experiments. So there is dispersion, and electrons inside the Fermi surface have negative E. The Fermi surface of an E is exactly 0, and electrons outside have a positive E. And this little e is related to the big E linearly. And I should have mentioned in the black hole problem, big E is the electric field on the surface of the black hole. So it seems like if you just naively think of adding a Fermi surface to this model, you need different types of black holes depending on whether you're inside or outside the Fermi surface. Well, I'm not studying black holes, so I'm just going to make an ansatz. I'm just going to say what you want to put here is not the average E, you just take the E of each electron and put it in there. So there it is. So imagine the electrons have some approximately well-defined momentum k, and there's some Ek that experimentalists can measure in different experiments. So you give me an Ek, and I give you the electron Green's function. It's exactly the SYK Green's function. And now it depends on this U, this interaction U, which I don't know. Okay, but everything else is fixed. So you've done your experiments, you've given me an Ek by photoemission. I don't know U, and I just put it in this, and I have an expression for the electron Green's function, which has some dispersion. And the way it has dispersion is I'm just taking a series of SYK models, one for each momentum shell, each one of which is related to a black hole with a different electric field on its boundary. Okay. Then I just plug this formula into the Kubo formula and compute the resistivity. Okay. Long story short, what happens is that the U cancels out, hooray, because I don't know what U is. And it cancels out because there's a cancellation between the density of states and the prefactor of this Green's function. So it cancels out, and the formula you get, resistivity, is almost exactly what's seen in experiments. So this alpha was the number which varied between 0.5 and 1. We get a number of 1.11. And this just drops out of exactly this kind of ansatz. Then you might ask, okay, that's great, you have an ansatz. Is it the solution of anything? So it is a solution of an extended SYK model, where you have some dispersion here, and you have this interaction which depends on the momentum. It's a random function of momentum and of the orbital labels. So it's some kind of model like this, where the interactions now also between dots. And then, somewhat by hand, but you can kind of justify it, you demand that the average of the interaction obeys a resonance condition. That is, you only allow for even virtual interactions that are exactly resonant. Now, of course, those are the most important, but you assume that all the other ones have already been absorbed into redefinition of Ek. So you only keep resonant processes in the SYK interaction. And when you do that, you can prove that this ansatz that we wrote down, which works so beautifully in comparison to experiments, is exactly the solution of this resonant model, where you have this additional condition where you conserve total energy in the interaction itself. Okay, so that's the end of my talk. So first part of my talk, I talked about the complex SYK model, which realizes this critical state as a function of charge or chemical potential. And so that gives us very useful knobs to study it, and in particular study its most exotic feature, which is the fact that it has a zero temperature entropy. And this would be manifested in the linear temperature behavior of the chemical potential or the non-zero thermal power at low enough temperatures. And then just mention some earlier work on resonant SYK models, which look to be at least a very optimistic description of linear anti-resistivity in correlated materials. Thank you.